Okay, welcome back everyone to the afternoon session, and apologies for the technical delay. Please welcome our next speaker, Ananda Roy from Rutgers.
Thank you. Sorry about the delay. There was something that went wrong, but looks like it's working now. So let me begin with a confession that I do not work on strongly correlated systems, although talking to Shovik over lunch is making me second guess my opinion. So I probably do, but don't know it. So I think, and also I'm very happy to be here to learn all the new subjects that has been spoken about. And my goal is to tell you about entanglement in strongly correlated systems. And this is not particularly easy because we don't exactly know to what extent strong correlations really show up in entanglement. But I will do my best and to convey at least some basic properties of entanglement measures and how they can be applied to many body systems. And so the best starting point is to start with the definition. And so I will begin with some definitions of entanglement that I'm sure all of you know, but just in case you haven't seen this in a while. So so we will have this setup that the many body system that you are looking at has a tensor product Hilbert space. So it means that if you have for n particle or the Hilbert space is of this form. And so on the lattice, if you think about doing lattice simulations, it's quite clear that if you would have spins or something like that, and then you would have tensor product structure, but this is not always allowed. So very simple examples are, for instance, if you have models with local symmetries like gauge symmetries, or if you have quantum field theories, then in these models, such kind of sharp bipartitioning of the Hilbert space into different blocks is not something that is physical. But for now, we will just say that this is okay. This is the best we can do. Okay. And then for pure states, so any state that you can write in this many-body Hilbert space can be written in this way. This is, of course, something that we understand, and here, this is the tensor product structure that you are seeing right here. And the definition of entanglement for pure states is that psi could not be written as written in this tensor product form. This is just a definition that I'm sure you have seen before. And the question is, what can we say in general? So this is a pure state is a special case, of course. And so the general statement is that for mixed states, rho is entangled if rho could not be written in this way. So it could not be written as a sum over tensor product of density matrices. Notice that there is a sum, and the sum over the PIs add up to 1. And so, and I hope this is clear, this is the density matrix for the first subsystem. and so on. So with this definition, we can already write down some examples. And so the first example that comes to mind that is very popular in the quantum information community is the so-called Bell state. And so there are 4 such states. These are entangled states of 2 qubits. So they are broken up into 2 kinds of families. So there is 0, 0 plus 1, 1. And here 0 and 1 are the sorry, there's plus minus. Zeros and ones are the 2 states of this 2-level system that you can think of it as a qubit, or 2 levels of any kind of electronic states, something like that. And there is another one which is written in this way. So these are examples of entangled states, and they happen to also be maximally entangled states of 2-qubit systems. So the other example that I wanted to give is that of a mixed state. And so I want to stick to this 2-qubit or 2-spin system. And so the most natural candidate that you can imagine is the one that is not entangled. So there is a state which is called a GHZ state. So it's written in this way. It has 3 spins, and it is a pure state of 3 qubits. It is a very natural generalization of the phi plus that is written right above. Now, if you trace out let's say the last spin, which is denoted by C, then rho AB will be given in this way. And you can see that this is exactly the convex sum that I wrote down right here. It's exactly in this form. And so you can see that the most natural candidate that you could probably right away think of is actually not an entangled state. And so the example that you do want to look at is what is called the W state. So the W state is given in this way. And now we can trace out the last spin. And the calculation is quite simple. So one can just work through it, and you will find that you will get this answer. So this term comes from the first state of the superposition. And then we have terms coming from here. And so you will find that you will get essentially this sum. So this looks like a complicated sum, but it's actually not that bad. And it turns out this is actually just a statistical mixture of 0, 0, 0, 0, and the Bell state that we learned about earlier. So the psi plus. And now you see this sum is actually something that you could not write as a decomposition of a convex sum over decomposition of density matrices, because you have an entangled state in the superposition in the second term, the psi plus. And this is something that's quite special about quantum states and quantum density matrices. If you think of classical probability distributions, and the previous definition of an entangled state was really given motivated by the properties of classical probability distributions, that if you have two probability distributions, then the total probability distribution can always be written in such a convex sum. So you can have the sum over some pi times the two probability distributions. And this is exactly the thing that is different in the quantum domain. Okay. Yes. Yes. Yeah. Because it can be written in this state, can be written as 0, 1/2 times 0, 0 tensor 0, 0 plus 1/2 times 1, 1 tensor 1, 1. So this is like the summation that I was mentioning, which is where sum over pi, rho 1I tensor rho 2I. So you can write it as a sum like that. Does that make sense? So the rho 1I is 0, 0, rho 1, 1 is 0, 0, rho 2, 1 is 0, 0, and the rho 2, 2 and the rho 1, 2 are these two. So you see, just a sum over the density matrices. And this is not the case in the second one. In this case, you actually could not break up this term, you could not break up as some tensor product of density matrices. That is the main point. Why this is actually an entangled state. So for mixed states, this is an example. It's probably the simplest example. Is it clear? Are the definitions clear? And are the examples clear? Okay, so this is the definition, but it's not particularly useful. So we say that you cannot write a given state in a certain way, and then obviously you're not expected to now start using trial and error to kind of find out if a state is entangled or not. So what you would like to do is to have some kind of operational definition where you are given a state and you compute something. And so this gives rise to the notion of what is called the entanglement measure. So whenever we have learned about entangled states, like Bell states, we learned that there is the outcome of that is that there is some correlation between local observables. This is something that we learned. There is something to do with correlation. But now we want to actually go a step further and come up with some entanglement measures which can really quantify entanglement. And so the first natural candidate that we have is known as the von Neumann entropy. So it is defined in the following way. So you imagine that there is a big system. It's broken up into two parts. There's A and B. And the rho A is the reduced density matrix of the total system. And then the von Neumann entropy SA is defined as trace of rho A log rho A. And this works extremely well for pure states. So for instance, if you have a given pure state, you can always do what is called the Schmidt decomposition. So it says that psi AB can be written as a sum over some coefficients times some tensor product of some bases. Okay, these are the psi I and the phi I are the bases in the two subsystems, A and B, and the psi AB can be written as a sum like that. Lambda i's are all non-negative. And this is known as the Schmidt decomposition. Given that the bases are orthonormal, then we can immediately write down the eigenvalues of the density matrices rho A and rho B. They are just given by the lambda i's. You can try to just do this, compute the reduced density matrix by first writing down the density matrix and tracing out, let's say, the B part, and then you will immediately see that the eigenvalues are indeed the lambda i's. And once the eigenvalues are lambda i's, then we can write down the von Neumann entropy extremely quickly. So we can just look at the entropy in the diagonal basis. So you can think of it in this way. And this immediately gives you the von Neumann entropy in terms of the eigenvalues. And so this von Neumann entropy has some meaning. And so there is an operational meaning that is very information theoretic, which is the fact that it can be viewed as the number of qubits that you need to transmit quantum states that are emitted by a statistical source. So this really is a generalization of Shannon's theorem. So there is an operational meaning for it, and this I think is not probably super important for this for you, but let me just make a note here. And this is Schumacher's theorem, 1995, that SA quantifies the number of qubits needed to reliably transmit by a statistical source. It's probably more beneficial to look at the classical analog of this. And so perhaps many of you can already recognize that this quantity here looks very much like the classical Shannon entropy. So the second note about the von Neumann entropy is that it's the quantum analog of Shannon entropy. And what does Shannon entropy say? Well, the Shannon entropy is actually essentially was coined in Shannon's first theorem, which says that the Shannon entropy for a probability distribution is given in this way. And it means exactly the same thing in the classical domain. It means that if you have a classical noise source that is producing, let's say, bits like zeros and ones with some probability, then you need, how many bits do you need to reliably encode the information is actually given exactly by the Shannon entropy. It's conceptually quite interesting. And for those of you who have not encountered this, let me give you a simple, fun example. That imagine that there is a noise source, which is my antenna right here, and it's emitting the symbols 0, 1, 2, and 3. Okay. And how many bits do you think you need to encode the information emitted by the source? 2 bits, yes. So you can say that this is encoded in 0, 0, this is encoded in 0, 1, 1, 0, and 1, 1, right? But The thing is, when we said this, we did not use the information about what is the probability of emission of, let's say, 0. What is the probability of emission of 1? And so so you can use that information. If you imagine that 0 was emitted with probability 1/2, and 1 was emitted with probability, let's say, 1/4, and 2 was emitted with probability 1/8, and 3 with 1/8, then this encoding that we said, that we wrote down there in terms of 2 bits is actually not the most efficient. So you can calculate this. And you can see that the Shannon entropy here is actually going to be less than the 2 bits that you have written down there. So here, just so that we are on this in the same notation, so let's define the Shannon entropy in base 2, so that we have actually just numbers and not unnecessary factors of log 2 that show up. This is a fun example, and you can work it out. So what we have learned so far is that there is something called von Neumann entropy, and for pure states, we can compute it using the Schmidt decomposition, and we arrive at this formula where lambda i's are the eigenvalues of the reduced density matrix for A, and it looks very much like the Shannon entropy. But even though it looks so similar, there are some fundamental differences. And one of the most interesting differences is that if you have a complex system with 2 parts, A and B, then SA can be actually bigger than SA union B. So imagine that the total system is in a pure state, but there is entanglement between A and B. Then SA union B is going to be 0 for A union B in pure state. But SA will be non-zero if A and B are entangled. And this is actually something that can never, ever happen for classical probability distributions. If you have 2 random variables, then the probability distribution for the 2 random variables, the entropy, the Shannon entropy for the 2 random variables would be always bigger than or equal to 1 of them. That's something that's very important. In fact, the SA bigger than or equal, bigger than SA union B can only happen if A and B are entangled. So there is a criterion for that as well. So let me give you a simple example for the Bell state again. So where we can compute the von Neumann entropy very easily. So this is the Bell state. So if you just work out the reduced density matrix, and this is very elementary, so I will just write down the answer. So the reduced density matrix is given by this diagonal matrix, and this implies that the von Neumann entropy is going to be log 2. This is a very simple example. Is it all so far making sense? It's all pretty basic, and we will hopefully move on to more difficult things soon. Any questions so far? Yeah.
So is there no notion for the entropy of the pure state without specifying what the partition is?
So the pure state has always entropy 0. And why is that?
Eigenvalue just 1, so then 1 and 0.
Yeah. Good.
No, but I mean, is there some obvious way to get the maximum entanglement entropy or von Neumann entropy of a pure state just by knowing what the partition, or you have to guess the partition?
you cannot, yeah, there is no way to figure out the partitioning based on the entropy. But in some specific examples like Bell states, by trial and error or prior experience, we can know. But it's not immediately obvious for general systems.
So in this mixed composition, what if A and B has different, different dimensions in the Hilbert space?
Then you just pad the remaining Schmidt values with 0. You say that the ones that are, you go for the ones that are non-zero and say that the others are 0. And it doesn't matter why.
So you're always able to decompose it into less than
the smallest dimension, yes. But even if you took all of them and took it to be 0, it would not matter. That's my claim. Because if lambdas are 0, so 0 log 0 is 0. There we go. Good. Yes.
Much more simple question. So,
And I love
of
simple.
course, earlier, the Bell state is, of course, the maximally intended state of 2 qubits.
Yeah.
Is the double state the maximally intended state 3 qubits?
No, well, maybe in this kind of maximal entanglement is defined for 2 qubits. For 3 qubits, you can kind of, but then you have to determine the kind of partitioning. So the W is the analog of.
I know there are issues with like monogamy. And
Yes, exactly. So
it's
I would
not-
not, yeah, I would not go too far along that direction. Yeah. Would you say that again? You are getting less information, look, but you're seeing that there's absolutely no understanding of what the state of A is. We are getting equal probability of 0 and 1. This is exactly what you're seeing. Any other questions? This side is awfully quiet. You have your own screen. I can be here too. Is it okay? Good. You know, that now is the most interesting example. And I'm sorry that I could not for the life of me find the paper that worked it out for the first time. So I will just write it down. And, you know, if you find the paper that does it, let me know. So this is the paper essentially discussed how von Neumann entropy is insufficient for quantifying entanglement for mixed states. And so I'm going to write down 3 states, okay? That's state A, then state B is so let me so these are the 3 states. So the first state is just a Bell state, and you can clearly see it's a pure state. Then the next stage is a statistical mixture of 0, 0, and 1, 1. And the other one is the maximally mixed state. Okay. So now let us see what the reduced density matrices for row A in each case is. So row A for the first one, we already wrote it, so I'm going to just write it down again. What do you think is the next one? Just trace out B, and it's hopefully clear that the first position is reserved for A and the second position is reserved for B. Sorry? I mean, I want to write a matrix for the subsystem A. It's a 2 by 2 matrix. What should I write? No,
Is it the same?
it is the same. So you see, when you do the partial trace, the first term will give you the zeros will just drop off. And then the second one, the ones will again drop off because of the overlap. And what about the last one? It's again the same because this is already in a tensor product form. Now you see the problem because now SA is log 2 in all of them. But you can see that clearly they are clearly not having the same amount of entanglement, right? Especially if you look at the first and the last one, it's evident. And so there is something that can distinguish between the three cases, and this is called mutual information. So let us quickly define what mutual information is. It's a very simple quantity. It is defined as the sum over SA plus SB minus SA union B. Okay, so now what do you think mutual information is for the first case? Two log 2. So the way to think about it is that the system is pure, so there is no entropy from SA union B, and SA and SB are going to be both the same. What about the next one? The next one, you will see that SA and SB will both again be log 2, but the total entropy now is non-zero. It's actually log 2. So if you take one log 2 away, then you are left with just log 2. And what about the last one? Is 0. Because now the entropy of the total system is actually going to be, I'm sorry, you don't see this, right? This Z is blocking everything, so, like that. It's okay. So so you see the SA union B will now be 2 log 2 because it's a maximally mixed state. So log 4 is 2 log 2. And so you see the mutual information is actually 0 in the last case. So you see that the mutual information actually goes down as you decrease the amount of correlation. So you started with a maximally mixed state, sorry, maximally entangled state. And then you went to a state that is not maximally mixed, but it's somewhere in between. And then you have the maximally mixed state. And you see that the mutual information is just going down. And so there is an entity that is actually erasing the correlation, right? What we learn is that the information is physical. That's actually one of the main reasons why laptops consume power. And so what is the work that is being done? And what information is actually being erased as you go from the state on the far left to the state on the far right? So if I wanted to go from the state on the far left to the middle state, imagine that you have the state phi plus, and then there is some entity who is randomly applying either identity or the ZA. So this is the Pauli matrix on the eighth subsystem. So in case it's not clear, phi plus, when you apply ZA, becomes phi minus. And if you do it in random, then the state phi plus would become a superposition of phi plus plus phi minus. And see, this entity has a choice. He can either pick identity or he can pick Z on the first subsystem. There's just one bit of information that he's using by picking the operator. And that one bit of information is actually being erased. And so this statistical mixture, if you just work out the expressions, you will find that it really is just this state. So this erasure of information is done by the application, the work that is being done by the application of identity or ZA. Is this point clear? Yeah. Well, there is certainly relative entropy. There is something called relative entropy that exists in both classical and quantum domain. We not introduce more objects, but I think the mutual information is something that is kind of useful, as we will see later on for macroscopic systems. They kind of tend to cancel out the so-called area law term. So that's one of the reasons why it's kind of popular. And so if you go now one step further, if you wanted to go from B to C, you just need to play the same game, but now apply identity or XA at random. And this XA is the probability, is the Pauli X for A. And then I will not work it out, but you can see that this will lead to just a maximally mixed state. So again, here this choice of one bit here and one bit here. Those are the two bits that you erased. So you see that we have mutual information that is somehow able to distinguish between states that are mixed, and there clearly is some understanding of what is an entangled state. But now we have encountered a problem. The problem is that we just wrote down a few slides ago that a state is entangled if this is true. And this was the reason why we had said that this state is actually not entangled. And now we have this problem that if we look at now mutual information, we see that mutual information is non-zero here and here, although this state is not entangled, as is this one. So mutual information is providing me non-zero answers, even though the two states are not entangled. And so we need something better. We need to go beyond mutual information. That is the main message.
You're imposing that it's not entangled, you cannot get information.
How did you arrive at that point?
Saying less mutual information, less entangled that mutual information was zero. We're trying to find a quantity that distinguishes.
Right. So I'm trying to find a quantity that says that non-zero for entangled states and zero for non-entangled separable states. Yes.
This mutual information
He's not doing that.
is not.
No.
What does it do?
So that's the funny thing. So and you know the understanding is that this it is giving me something here, right? And what is it? It's actually classical information. So it's what is called a C bit, a classical bit of information. And here actually we have one entangled bit of entanglement bit plus one C bit. So a Bell state actually has two bits of information. One bit is actually from the entanglement, and the other bit is classical correlation. And mutual information is actually giving me the classical bit of information. Yeah, but I wouldn't say that, but you can if you want. There was another hand. Yes.
We do have the mutual information being zero.
Right. So it somehow sees that when things are totally mixed, then we still get some information, some knowledge about so some knowledge about the state being not entangled. So it.
Because it's zero, I can guess that it is actually maximally mixed.
In this case, definitely. Yes. In general, don't know. I would think about that.
Or at least I can narrow down my list of
Yeah, yeah,
density.
certainly, certainly.
I have another
Yeah,
question.
yeah.
So when you were talking about the process to go from A to B and B to C,
Mhm.
just to understand it better, say if I had some other Bell state as A,
Mhm.
then would I have used some other polymetric?
Yes, yes. And you would always have applied at random either identity or some Pauli operator, and that would give rise to the state in the middle. Yes.
One thing that's right then is, considering like a large computational system, with however much you can, we're looking for kind of a witness where you continue to like randomly do measurements on your large system. Eventually you'll reach no entanglement. You're trying to find out where that when happens. So,
You could think of it like that. That's a fine way to think about it. Yeah.
So if I start from the Bell state by state, and I don't excuse me, I don't actually mix things. I just reduce the entanglement while keeping it as a 1 and 2 state. The mutual-
Which of the
the one on the left.
on the left?
Okay, so I'm not actually mixing things, I'm just reducing the entanglement a bit and adding on some other 1 to 2 state. The mutual information that's associated. Will I lose information symmetrically between the E bit piece and the C bit piece, or will one of those die off first?
This has to be worked out. It's I don't remember. So you know the maximally mixed state. So you can write down, of course, a state which is cosine theta 0, 0 plus sine theta 1, 1, right? And then if you plot it, you will find that there is some kind of a concave function, and it's maximum. The entropy is maximum exactly in the middle, which is theta equals pi over 4, right? And then you can compute the entropy for all values of theta, and then you can see. I don't remember the answer, but it's a very simple calculation. One can do this. But it's a good question. Any other questions? Yeah.
So I understand correctly, the maximally entangled is not fully entangled, then, right? You're saying that there is classical information wrapped up in the entanglement. Is that
It just comes hand in hand. It is entangled, and it's just a mutual information. It's picking up something more. It's picking up classical correlation on top of quantum correlation.
so it's just the mutual information that has this classical component. It's
Right.
not reflective of.
Exactly. Exactly. Any other questions? Okay, so if there are no more questions, at least I guess it's enough motivation to look for some better measure of entanglement for mixed states. And so this is the other thing that I wanted to discuss for measures of entanglement, and it is called the entanglement negativity. Is everything okay? Okay. Now, I think you probably want to turn up the audio. Good. So an entanglement negativity is something that was proposed by Vidal and Warner in 2004. And this was based on the seminal work by Asher Perez in 1996, where he essentially formulated once and for all the separability criterion. So this is the necessary and sufficient condition. So this is how it goes. So if rho AB is separable, that is not entangled, then the new matrix rho AB partial transpose B defined as what? I'll tell you in a second. Let me just write it because it's I wish I had made slides. So if rho AB is separable, that is not entangled, then the new matrix rho AB, and then you have a T subscript B, that's partial transposition with respect to the Bth subsystem. It is nothing scary. It just says that if you have M and mu, you just switch the mu and mu, you switch the mu and mu on this side. Okay, the bras go to Ketz for the second subsystem only. So you just switch these two on the right hand side. So then to complete the sentence, the new matrix rho AB TB defined like this is also a valid density matrix. Now you have to tell me what a valid density matrix is. Who knows what a valid density matrix is? Okay. Well, trace is one. And
trace of rho
and
square.
positive. Positive. Trace of rho square is less than or equal to 1, that's true, but the positive matrix. And positive matrix means that it has non-negative eigenvalues. And you can convince yourself from this simple formula that this partial transposition actually does not change the trace, because mu and the nu are the same for the trace case. So then we just need to look at the fact that the eigenvalues are non-negative. And this is the Paris criterion that tells us if a mixed state is entangled or not. Yes. I give some examples. Okay. Then I don't think there is a very clear physical understanding of this, especially in the many-body context, but I try to say something. So to give some examples, so we have identity A over 2 tensor identity B over 2. This is the case that was called C before. And so here now you see that the partial transposition with respect to B will clearly not change anything. It's a diagonal matrix in the second half, right? So rho AB TB is actually just rho AB. So we see that the partial transposition leads to the same matrix. Clearly it has non-negative eigenvalues. So this is clearly a separable state. there's the next case that we discussed, which is 0, 0, 0, 0 plus 1, 1, 1, 1. And now, here again, the exercise is very simple. If you take the partial transposition, all you have to do is to switch these two and these two. And what do you get? The same. So again, there is no change. And you should notice that even though in these specific cases, you actually have after transposition, you get back the same density matrix, but that is not what Paris told us. We talked about non-negative eigenvalues, but in this case, it's an even stronger statement, right? So. And finally, we have the density matrix that I will write down a slightly more general density matrix. It is written in this way. These are called Warner states. You can check that the trace is 1 for this, and p equals 1 corresponds to the case when it's just a Bell state. The last term drops away. And this is just a 4x4 matrix. And if you have not done this before, I really suggest that you compute the eigenvalues of this 4x4 matrix. It's very simple. And clearly p here is less than or equal to 1. If you compute the eigenvalues, you will find that there are 3 that are the same. And then, so there's 1 minus p over 4, and then there's 1 plus 3p over 4. These are just the eigenvalues of the density matrix. I have not done partial transposition yet. So it's just the simplest case. Now, if you do the partial transposition, then you can, if you compute the eigenvalues, so maybe before computing the eigenvalues, let me write down the 4x4 matrix that I have here. This is the 4x4 matrix. And you can compute its eigenvalues. And the eigenvalues now you will find, first, you can check that this is not the same as row AB anyway, that you can easily check. And you will find that the eigenvalues are now now the eigenvalues are 1 plus p over 4. 3 times, these are all positive. But this is 1 minus 3p over 4. So you now find that actually in this case, if you do the partial transposition, the new density matrix will have actually negative eigenvalues for p bigger than 1/3.
What about the converse of the criterion? So if we do this operation and we get the valid density matrix, does that tell us nothing about the entanglement?
It tells us that the state is separable. It's necessary and sufficient. I think I said it in words, but didn't write it. So this is necessary and sufficient. It goes both ways. 5 minutes? Wow. I'm not even halfway through. Okay, so, okay, well, so as you can imagine, there is a negative eigenvalue for the density matrix. And so Vidal and Warner very creatively called this the entanglement negativity. So the negativity is defined as and this summation is a sum over negative eigenvalues. So in the previous case, for instance, the negativity would be 1 minus 3p over 4. And it's conceptually actually quite interesting because these Warner states are used in quantum information quite a bit. And maybe some of you know that there is something called the Bell inequality that has to be violated to unambiguously establish the quantum nature of the correlation. And it turns out that the Bell inequality is violated for p bigger than or equal to 1 over square root 2. 1 over square root 2 is 0.7. So that means that although the state starts to be entangled at 1/3, you have to go up to 1 over square root 2 before you can actually violate the Bell inequality, the classical bound of the Bell inequality. Okay, yes.
So when p is smaller than 1/3, it's this rho AP set.
Yes.
The number you wrote down at the end of the transpose was already given.
Well, it is called so you compute it by taking the partial transpose, but you call it the negativity of rho. There was a, yeah.
You mentioned that the inequality is violated for greater than 0.7.
Yeah.
But this separability condition breaks down for over 1. So what can I, is it a classical entanglement between those two?
No, it's just that the entanglement is not enough to violate the CHSH inequality. There is some inequality that was proposed to really show, and the entanglement is not enough to establish that the state is not classically correlated. It's just that it's a continuum, you know, it's not like there's entanglement or not. There's a continuum. Yeah.
Here two qubits. The maximum entanglement state only in 1/3. So how many qubits need to get so actually?
But that's a more difficult question. So you're asking if there are, so you want to ask that if you had many copies of such Bell states with let's say 1/3
Right.
p, how can you get to 1 over square root of 7? Yeah, that will require more work. I cannot tell you right now, but this is entanglement distillation. It is well understood, but I just don't know the answer off the top of my head. But it's a very good question. This is very, very delicate stuff. Yeah. Okay. Any other questions? I think I am pretty much I have like 1 or 2 minutes, right? So let me just, not go into the next thing, but if there are more questions, I can answer. Yeah. Yeah, sorry, there is some ambiguity here. So of rho AB TB. So lambda I here is not the eigenvalue of rho AB, but rho AB TB. Thank you.
So I found one of the previous pages said that the A, for example, was entangled.
Yeah.
Like then if you have P 0, that's when you remember the A state.
No, P is 1. So P is 1, right? So in this case, P is 1 is the Bell state. Then this big 1 is bigger than 1. Okay, so there's one more. Yes. Sorry.